Okay, we are almost ready to get to the fun stuff, which is actually using all of these tools about continuous distributions to test hypothesis and estimate parameters that we can use to make inferences about what we're observing in the real world. But there's a couple of final things that I wanted to go over. So today we're going to go over moments. We're going to go over tests for normality, with the caveat that we probably shouldn't put too much stake at all in any of these tests for normality. And then I want to talk about transformations. So let's start with moments. Things like the mean and the standard deviation, those are what statisticians and mathematicians like to refer to as central moments. And we don't need to get really into the details. I know on the handout I provided a little bit of the math behind moments, but we don't really need to worry too much about those details. The first central moment is equal to 0, which is kind of interesting because in a standard normal distribution, the mean is 0, and that's where we solve for the first derivative equaling 0, the slope equaling 0. The second central moment turns out that that's the variance. And lo and behold, if you were to take the second derivative and calculate the value at which the slope of the rate of change is equal to 0, that's going to be the variance. And so there are higher moments. In particular, there's the third and the fourth moment. And I just wanted to briefly go over what those were about. And you, again, don't have to worry about calling them the moments or remembering that something is the third moment, something is the fourth moment. What I really want to think about is descriptors that we can use to say something about whether or not our data look to be normal or not. And so one important little piece of housekeeping I want to do first, because I don't think that we've done this yet, is installing packages in R. So as I mentioned when I introduced R has this enormous user community, and so far we've just been using stuff that is part of base R, stuff that just always comes with R. So the functions that we've had, like mean and median and any of those things, or sample or the for loops and all that stuff, that's all part of base R. But R has an enormous library, basically, of different packages that you can download, and that way you can call those particular functions. And over the course of the semester, we're going to be downloading a number of different packages. So I just want to really briefly go over how one might do such a thing. And so the first package that we are going to play with is called E1071. Usually the packages have names that are a little bit more descriptive than that. I don't remember even why that one's called E1071. But I already have it on my computer. And so if I were to just type in library and then in quotes E1071, that's going to load in the package E1071, which is going to give me functions that wouldn't otherwise be available. So how you would install this is if you go to packages down here and then you say install, it might ask you for what repository to use, and I always just use the cloud one, the top one. But what you would do is you would type in the package that you want. So for example, I could type in E1071, and then all I have to do is say install, and it'll be put into the appropriate path, so that way in the future all you have to do is type library E1071, and then those functions will be in your workspace. When you're doing this, make sure that install dependencies is checkmarked. A lot of R packages will call other R packages, which means that you might think that you're just installing one, but you might end up installing 5 or 6 other packages if a particular package is calling other libraries. Okay, and so I just wanted to do that because over the course of the semester, as I said, we will be doing a number of installations of different packages, because different packages are going to have basically different tools that we can use when we are playing with our data. Right. Okay. So I'm going to just call in 1071, and within 1071, there's a couple of functions that we can look at that will describe how our distribution might be different from a normal distribution. And the first moment then that I want to think about that's describing our normal distribution is the third central moment, which refers to or will describe what's called skewness. And skewness is how much the data are basically off-center. If one tail is longer than another tail, then you would say that that distribution is skewed. And so I am going to simulate some data that is skewed. And this is the same stuff that you have from the notes that I've posted or the R script that I've posted. I want to say this very, very clearly. Do not worry about the details with R gamma. R gamma, I'm calling up a gamma distribution. We are not going to deal with gamma distributions. In the future, you might deal with gamma distributions and you might decide you absolutely love the gamma distribution. For our purposes, we don't need to worry about what the gamma distribution is. I just happen to know that the gamma distribution will generate a skewed distribution for me. So that's what I'm going to call up. So I'm going to just take 10,000 random variables from a gamma distribution, and let's just look and see what those data look like. I'm going to go ahead and I'm going to make a histogram, and I'm going to do a histogram of those random variables, and then I'm going to say breaks equals 100, which is just going to give 100 little bins that it's going to populate. And there's the histogram of my data. And so we would look at this and we would see that this tail is clearly a lot larger than this tail, and so we would say that it is skewed. And another way that we can show the same thing, if we wanted to smooth this out and have it look like a curve, is we could say plot and then plot what? The density. And density will basically provide you with a plot that'll be a smoothed out curve as opposed to being a histogram. So I'm going to say I wanted to do the density of x, and then I'm going to say adjust equals 2. That's just the smoothing kernel for how it's drawing the curve. Again, these are little details that you really don't have to sweat. It's just I wanted to explain what my code meant because I was really keen on making this beautiful, beautiful little picture here. Okay, and so let's first think about why we might be concerned about skewed data. And again, if we're going to decide that we're going to model our data as being random variables drawn from a normal distribution, we would really like for those data to be as normal as possible. Remembering that all models are wrong, some models are useful. Let's make a useful model, and a useful model would be one where it's actually normal if we're going to model it as normal. But we could look at this distribution and let's calculate what the skewed mean is. So I'm going to create an object called skewed mean, and it's just simply going to be the mean of x. Okay, and so that would be my calculation of the mean if I had just collected all 10,000 of these random variables and calculated the mean. That's going to be the mean of that distribution. And so I'm going to go ahead and on this plot, I am going to plot it. Ab line. I want it to be a vertical line, and I want it to be at the skewed dot mean. And at this case, I will say color equals red, and I'll make it a fatter line, line width equals 2. And so this is the mean of those data. And again, that mean should be where the highest concentration of data are if the mean means what we really want the mean to mean. And that means that we would expect the mean to be 50% of the data should be below the mean and 50% of the data should be above the mean. And we could ask, well, is that really what the case is? So let's say p norm, and I will take my skewed dot mean, and I will say skewed dot mean for the mean, and the standard deviation of x. Okay, so I'm taking my observed mean, and then I'm putting it back in here again as though this were a normal distribution. And you'll see that it says 0.5. So in principle, if this were truly a normal distribution, we would expect 50% of the probability mass to be below the mean and 50% of the probability mass to be above the mean. Now again, I can use, since I use that gamma, which again, I don't want you to worry about too much, but I can use that same function for gamma, and I can ask, well, what really is the probability mass where I've calculated my mean? And it's 0.6. So in reality, 0.6 of the probability mass is over here on this side of the mean, which means that 40% of the probability mass is over here. So you can already see that we are violating the assumption. By violating the assumption of normality, we're already wrong about what we think the mean means. And this is why I often say you want to make sure that the mean means what you think the mean means, or else the mean isn't going to mean what you want it to mean. And this would be an example of where the mean is not going to mean what we want it to mean, because the mean should be right smack dab in the middle of our data. And right now, it's off center. It's over here to the left. For fun, we could say, well, maybe remember that there's other kind of location descriptors we could use. We could say, you know, what is the skewed median? Skewed dot median. Median, spell that correctly, Jim. So here's my skewed median, and I could take the median of x. And it's 1.701. So let's go ahead and I'll plot that. I'll abline it. Abline skewed median. And the skewed median will be a vertical line. Yeah, that's what I wanted to do. Okay, and so now it's shifted over here a little bit. And this might be a case where the median might actually do a better job than the mean when describing the data, since we have this skewed distribution. And so we could ask at what quantile, and again, we know this because we were the overlords in this simulation. So I can go back to my gamma distribution, and I could ask for the quantile where I'm at 0.5, given those two other parameters that are in the gamma, which again, you don't have to worry about. But this is the value where actually 50% of the data is below and 50% of the data is greater. And here you can see the median actually did a pretty good job of describing that location of where you expect 50% of the data to be. And it certainly performed better than the mean did, because the mean was off center so that 60% of the probability mass was on one side and then 40% was on the other. And so if we were to model this as a normal using our estimate of the mean, what are we really doing? We are assuming that that is actually what the distribution is that we're dealing with, right? And so the black line here is what our data actually are, but if we decide that we're going to model it as a normal with a known mean, you can see that, you know, why we're off is because this is what we're assuming the actual underlying distribution looks like, and in reality it's this black line. Okay, and so that's why we need to be careful with thinking about normality. And so now let's bring it back up to using a function from this library here, the E1071 library. And within that library there's a built-in function called Skewness. And what you can do is you can just put your data into that function. So our data are x, right? That's our simulated data. And we could go ahead and run that function, and we get a number. We don't need to worry about the details here, but you'll see that it's a positive number. And a positive number is telling us that our data are positively skewed, or we could think about that as being right skewed, because the right-hand side of this distribution has a longer tail than the left side of that distribution. Another way that we can look at this is by using what's called a QQ plot. And a QQ plot is a quantile by quantile plot. And so what it will do is on one axis, it'll show you the value of your actual data. And then on the other axis, we will say what the theoretical expectation is if our data were truly random variables drawn from a normal distribution. And so to do that, we can use a function called QQnorm, which I believe is just in the base package. And then we're going to give it our, our predicted or our sampled values. And what I'm going to do is I'm going to standardize them. So I'm going to take all of our random variables and I'm going to Z transform them. So that way the mean will be 0 and the standard deviation will be 1. Again, that's not going to change really what the distribution of our data look like. It'll just rescale it into units of standard deviation. So I'm going to scale x, and then I'm just going to add a few arguments in here to make the plot look nicer. So PCH is 19. Character expansion, I'm going to say is 0.5, so that way the dots are smaller. PCH 19 will give me solid dots as opposed to open circles. And again, this is just stuff that you'll learn as you just start playing with R. Obviously, you'll never be evaluated on your ability to make pretty plots. And then I'm going to go ahead and I'm going to put a line that is simply going to show what the expectation is for a one-to-one relationship. And so this black line here is where we would expect our data to fall if our data were actually random variables drawn from a normal distribution. These black dots are our actual data. And you'll see that when you get close to the tails, we are deviating greatly from what the theoretical expectation is. So when you're looking, as part of an exploratory data analysis, when you're just kind of checking out your data to figure out whether or not you're happy modeling it as a normal, a QQ plot can be a pretty handy way to do that. And we can see that clearly we are not on this one-to-one line where we would expect that relationship to be. And so we would look at that and we would say, I bet that our data are skewed. We could also look at what happens if it's skewed in the other direction. So to do this, I'm just going to say I'm going to make it left skewed, so I'm going to call it LX, and I'm just simply going to invert all the values of X, so that way it's going to be negatively skewed. And we can look and see what that would look like. Now we're dealing with this distribution, which clearly has a longer left tail than it has a right tail. So we would, just by eyeballing that, say that looks like it's left skewed to me. If we were to use that skewness function, you'll see now that it's a negative value, right? This is what it was when it was skewed to the right. This is what it is when it's skewed to the left. It's a negative value. That's telling you that it's left skewed. And let's go ahead and we can look at that quantile by quantile plot, the same as we did before. And now you can see that it's bowing in the opposite direction. Okay. So again, on the x-axis here, these are the theoretical quantiles. If the sample were truly normally distributed, we would expect our theoretical quantiles, what the probability density function of a normal tells us something should be, versus our actual sampled quantiles. And since it's left skewed, we have way more extreme negative values than we would expect by the theoretical expectation if our data were truly normally distributed. And so a QQ plot, again, if it's bowed in this direction, that's telling us something about the fact that our data are left skewed. And so that's skewness, and that is generally known as the third central moment. The fourth central moment is kurtosis, and kurtosis describes another way in which our data can deviate from a normal distribution in a way that might cause us to incorrectly estimate our parameters. And so kurtosis, again, is just describing the concentration of the data, and there's two different types of kurtosis. The first kind that we can talk about is what's called leptokurtic. And leptokurtic means that you have way too much concentration in the middle or at the mean compared to the tails. And so I'm going to just use a little hacky way here of just simulating some kurtotic data. Again, you don't need to stress the details here. And then I'm going to create an object called, I'm going to call it kurtos, apparently. And so now we can pretend that this is our sample. I don't know what we sampled, but we sampled something, and we sampled a lot of them. So we should feel good about all the hard work we've done. And so now we have this sample, and let's go ahead and let's just look at it. That's the first thing you should always do with your data. You should become really familiar and happy to type in HIST a lot, because it gives us an opportunity to take a peek at our data. And there's the peak of our data. So it's symmetrical. That might make us feel pretty good. Hey, that looks kind of normal-ish, but these are really, 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 really high here in the middle, which means that there's a lot of values that are really close to the middle and very little values that are over here on the side. And I'll do the same thing that I did with the skewed stuff, where I'm going to just plot the density to make it look like a nice little curve. And then that is what our data look like. So clearly eyeballing that to me looks like there's a problem there with being leptokurtic, because you have lots and lots of data there in the middle. And so let's see what the consequences of that might be. I'm going to take the mean and the standard deviation of our sample and naively assume that that our data are normally distributed, because maybe I forgot to do a histogram of it to take a look at it. And let's overlay on top of that what we'd be modeling our data as, right? So once we calculate this mean, which is 0.016, and once we calculate that standard deviation based upon our sample, we are modeling our data as random variables drawn from this red here, this normal distribution. And clearly we have way too much going on in the middle here and not nearly enough going on at the tails. And so we can again use the QQ plot method to kind of think about what our data might look like. So again, I'm going to rescale it so that way it's centered at 0. And I'm going to compare that to the theoretical expectation. And I'm going to plot my real data to what the data predict. So I do that. And now you see that it's kind of squiggly in this way, right? And that's telling us that we have data that have we have more extreme negative values than theoretically would be predicted. And here we're going above the theoretical prediction, now below, and now above. So we have this serpentine kind of pattern of what our data look like compared to the theoretical expectation. Easier way to do this is to again use a function from this E1071, and that function is going to be called kurtosis. And I will go ahead and I will put our data in there. Kurtos spelled correctly. And we get a positive number. If the data are not kurtotic at all, that value should be 0. We have a positive value, and that indicates that our data are leptokurtic, meaning that we have too much concentration in the middle compared to the tails. The other way that you can be kurtotic, besides leptokurtic, is to be what's called platykurtic. Platykurtic refers to situations where your tails are too fat compared to the center. And so I'm going to simulate some data that will be platykurtic. Here I'm going to use another distribution called the beta distribution. Don't worry about the details. I'm just showing you how I simulated this data. You can totally ignore it, because at the end of the day, all we care about is our sample, which is this, kurtos. And so let's take a look at what our sample looks like, since we sampled from a population that we know is platykurtic. So let's go ahead and we can make a histogram. And now you can see it's really like there's not as much going on maybe here as you would expect, and these tails seem seem pretty fat. And we can go ahead and make a curve out of that like we've done before using the plot density function. So that's what our data look like, and we're deciding that we are going to model that as a normal maybe. And so again, we'll calculate the mean of our sample and we'll calculate the standard deviation of our sample. And then as before, I'll lay on top of this what that normal distribution should look like based upon our estimate of the mean and our estimate of the standard deviation. And now you can see that the normal distribution has more concentration in the middle compared to the black here, which is our observed, and then we have more data on these tails than the normal distribution would predict. And we could go ahead and we could use the QQ plot method to take a look at, see what that looks like. And it also looks like a little squiggly snake here, except here it's in the other direction, okay, where our theoretical quantiles are on this line down here, but our theoretical quantiles are saying that there should be less observations at those extremes, whereas our observed data has more in the tails. And so you end up with this little serpentine pattern right here. And we can compare that against this situation where the little snaky went this way, okay? And that was telling us something about it being leptokurtic. If it's platykurtic, it goes this way, okay? So it's just basically flipped around. And we could go ahead and we could use that kurtosis function, and let's give it our new sample. And now it's a negative value, okay? Again, if the data were not kurtotic at all, we would expect that answer to be 0. The fact that it's a negative value is telling us that our data are platykurtic, which means that there's too much on the tails at the extremes. And so these are just descriptors of what your actual distribution looks like that you can use to make an assessment as to whether or not you're necessarily happy with modeling your data as being drawn from a normal distribution. And the more you can make your data normal, the better it'll be, because the more reliable or informative for predictive purposes your actual parameter estimates will be. And so that ends our little introduction to moments, to thinking about moments. And then next we'll think about tests for normality. All right, let's think a little bit about tests for normality. And I want to start with this really, really important thing. All tests for normality are not very good. And so whenever you run a test for normality, or if somebody asks you to run a test for normality, you should always take them with somewhat of a grain of salt. And there's lots and lots of different tests for normality that have been proposed. I'm going to mention 3. And 2 of those 3 I'm going to mention because they pop up a lot in the literature, so you should be somewhat familiar with them. And then one of those 3 is, I guess, the one that I feel most comfortable with, thinking that it's the better of all of them. But again, you should take all of these with a little bit of a grain of salt because they all have important weaknesses. And so the first one I want to mention is what's called the Shapiro-Wilks test. And it's a pretty commonly used test for normality. It has an important weakness in that it's really sensitive to sample size. So if you have a very small sample size, it tends to allow things to pass the test, even if the data are clearly not normal. And then if you have a really, really large sample size, it tends to claim that your data are not normal. So it tends to be really, really sensitive as you increase sample size. So let's kind of play around and think about how we might use that. And for this, we're going to have to use another library. And that library is called fbasics. Library fbasics. I'll add that when you install libraries on your computer, that doesn't mean that they're automatically loaded in when you turn on R. You're always going to have to call in these other packages. And so I'll go ahead, and then you can see it's telling me a little bit about it. Don't have to worry about these warning messages. It's just telling me that parts of it were made under a different version of R. It's not going to affect anything. And it actually looks like there is a function called kurtosis and skewness in the fbasics package, which is something maybe I should make a mental note of, that I don't need to use E1071. But and so after I load this in, I can I can use the built-in functions from fbasics, which include functions for testing for normality. So the first thing I'm going to do is I'm going to simulate some data. I'm going to set the seed as I always do, and then I'm going to just take 50 random draws from a normal distribution. And now I can test to ask whether or not these data are normal or not, right? We know that the underlying sampling distribution was normal because, again, we simulated it. We are the omnipotent beings. We know everything. And so we can go ahead and let's test for normal. So I'm going to say normal test is the name of the function that's in the fbasics package. I'm going to give it the data, and then I have to tell it what method I want it to use. And the method that I am going to use is SW, which stands for Shapiro-Wilk. And so I go ahead and I do that. And we get a test statistic, don't worry about that. And then we get a p-value. And we already talked a little bit about p-values. Since that p-value is below that arbitrary 0.05 threshold, we might say that it is significant. The null hypothesis here is that the data are drawn from a normal distribution. And so the alternative would be that the data are not drawn from a normal distribution. And thus, according to the Shapiro-Wilk normality test, our data are not normal. Which is kind of weird, right? Because we know that it should be normal because they were random variables drawn from a normal distribution. We did that here. And yet it's still telling us that our data are not normal. So here's an example of where the Shapiro-Wilks test is just being a little too sensitive to one or two data points. And I don't know if we're on the big end or the small end of the sensitivity to Shapiro-Wilk. But again, this is just kind of reiterating, all of these normality tests are not that great. They're all pretty flawed. And we should always take the results with a grain of salt. The next one that I want to talk about is called the Kolmogorov-Smirnov test. A lot of times you'll hear people refer to it as the vodka test because Smirnov is in the name here. And this is probably one of the more common ones that at least I see in the literature. And the sad thing is that it's probably one of the worst. This test was originally developed to compare just two distributions. So if you had two samples and you wanted to compare the distribution of those two samples, that's what this was originally invented for. What we use it for in this case is we take our observed data and we're going to compare it against the theoretical expectations and then ask how close our observed data are to those theoretical expectations. And so behind the scenes, what the Kolmogorov-Smirnov test is doing is it's basically using a QQ plot, where here's the theoretical expectations, and then here are the values for our actual samples. And what the Kolmogorov-Smirnov test is doing is asking basically how good of a job are we doing at keeping these lines on this line, on this solid line here, which is our theoretical expectation. And the more divergent these QQ plots are, you know, whether they looked like this or whether they looked like this, the more divergent they are from that theoretical expectation, the more different our sample is from a normal distribution, and the Kolmogorov-Smirnov test then does a statistical hypothesis test on that. So let's take a look and see how the KS test does with our data. And so just as before, I'm going to use this function called normal test, and now I'm going to say that the method equals what? KS. That is the argument for the Kolmogorov-Smirnov test. I will hit return. I will look down at it, and there we have the p-value associated with the test. So according to the KS test, our data are perfectly fine and normal. For our purposes, for testing for normality, you can ignore the less than or greater than. That's relevant if you have two empirical distributions that you're interested in. For our purposes, it's two-sided because there's two, you can think of it as you can be extremely different from normal in one way, or you can be extremely different from normal in another way. And that's really what this less than or greater than is to do with. And really what it has to do with is how many of the points are on the positive side, above the theoretical expectation, versus how many points and how far are they below the theoretical expectation. But for our purposes, all we really care about is this two-sided test. So the p-value is 0.57. So we walk away saying we'll accept the null hypothesis that our data are random variables drawn from a normal distribution. And so the final normal test that I want to mention, and if you're ever tempted to use a test for normality, and they're not necessarily a bad idea, it offers some kind of an objective way of thinking about, do we feel good about modeling our data as being drawn from a normal, is a test called the D'Augustine-Pearson omnibus test. And this one, again, is probably one of the better ones out there. This is the one I would recommend that you would use. And what it does is it does a statistical test on both skewness and kurtosis, and then it combines those two things together, both the amount of skewness and both the amount of kurtosis, and it asks overall, is it different from normal? And that's why the omnibus is there, because ultimately it's going to take skewness and kurtosis and come up with some kind of a test for normality. And so to do this, we can say normal test, our data again, the method is equal to dA. dA will do the D'Augustine-Pearson omnibus test. And so we do that, I get those annoying warnings again, and what do we got here? Well, let's look just at the statistical hypothesis testing part. So overall, our p-value is greater than 0.05, so we might be tempted to accept the null and say that our sample appears to be random variables drawn from a normal distribution. And then we also have skewness, and we have a p-value associated with kurtosis. And so that's kind of nice. Sometimes when you have real data, skewness might be significant, but overall, it might not be significant, so you're still happy with the data. But if skewness is significant, you could always just take a second look at your data and decide whether or not there's something you need to do to fix that problem. But in general, when we're doing the D'Agostino test, it's this omnibus test. And it's the omnibus test because it's including aspects of both skewness and kurtosis simultaneously. And it's giving us an assessment as to whether or not, or it's giving us a recommendation as to whether or not we should or should not accept the null hypothesis that our data are random variables. And so that's just the brief and only introduction to tests for normality. It's worth testing your data for normality just to get an idea of where it might be wrong. Again, all of these tests should be taken with a grain of salt. And if you are going to do the normality test, I like the DA test, the D'Agostino test, because it's giving us explicit information about skewness and kurtosis, as opposed to just giving us a yes or no, is it normal or not. And so that is the end of the test for normality. I want to also plant one more seed in your head when you're worried about testing your data for normality, is that people often talk about the assumption of normality being really important for statistical models, but as we'll see, that important assumption is that the leftover variation or the residual variation is normal. It's not as much about the actual data that go into the model being normal. And we'll talk about that a little bit more as we start to build models. We'll start to, as we do our quality control steps, we'll see what we want to take a look at and see whether or not it's normal or not. A lot of times your data will never be normal, and it can't be normal, and that is okay, because after you run the statistical model, the leftover variation will be normal. And we'll see that, and we'll play with that a little bit in the coming weeks, as you will. Okay, part 3 is coming up. Right. Now we'll get to the final little piece of housekeeping that we need to do, which is concerning transformations. And so a lot of times people feel kind of queasy about transforming their data because it seems like it's kind of cheating. It is cheating if you're using transformations doing what's called p-hacking. P-hacking is a disparaging term which refers to trying to kind of massage your data so that way you get a significant answer. But we're not going to worry about significant answers in this class because, as we'll see next week or in a couple of days, that we have to think really carefully about what we mean about significant. But people often feel kind of weird about it because it feels like it's cheating. Like somehow you're changing your data and that's kind of cheating. But there's really no reason why we need to feel that way. As humans, we feel really good about putting things on a base 10 scale. And one could imagine that there's some reasons why we think a base 10 scale is the correct scale that we would want to measure things on. I'm sure if you think about it really hard, there's probably reasons why humans might really like a base 10 scale, that it makes perfect sense. Coincidentally, humans have 10 fingers. And so our whole universe, when we're counting numbers, it makes perfect sense that we are doing things as a base 10 scale. But there's already a lot of measurements that we use in science that are not on a base 10 scale, and we don't even think about it. So when we're thinking about the number of hydrogen ions flipping around through a solution, when we count those hydrogen ions, that's how we calculate the pH. But the pH is actually on a log scale. It's the log number of dissociated hydrogen ions. It's not the actual number, which means that the difference between a pH of 5 and 6 is an order of magnitude smaller than the difference between a pH of 6 and 7. The Richter scale is another example of a scale that people feel pretty comfortable about talking about when they're talking about earthquakes, but that's also on a log scale. Magnitude 5 versus magnitude 6 is a smaller difference than 6 and 7. The difference between a magnitude 6 and a magnitude 7 earthquake is an order of magnitude larger. And so these are things that we already have that are on a log scale, but because they're kind of familiar and we use them, especially pH, we use, in most science labs at some point, we feel really comfortable just thinking about those as numbers that are describing the acidity or the basicness of a solution without maybe ever really appreciating, except obviously when you have to do it in chemistry class, that it's actually on a log scale. And so I don't think that we need to feel creepy or anything like that when we decide to transform our data, if by transforming our data it meets the assumptions of normality. So I just want to talk about a couple of transformations that are common transformations that people use. And the first group of transformations are what are called power transformations. And power transformations would be something like looking at all of your data and deciding that if you were to take the square root of all of those values, that your distribution would actually look a lot more normal. And then that's fine. You've just changed the units at which you have that you're dealing with your response variable. So no longer in the raw units, now they're in the square root of those units. And likewise, you could take the cube root. And there's certain situations where it makes sense that you would do these transformations. Say that you had a response variable that was already in squared terms. So the area, if you were keeping track of square meters, and then that was the data that you actually had calculated was square meters, it might make sense that if you were to take the square root of that, then it would be, just in simple units. And if we think about how area increases, right, when it's like 1 meter by 1 meter versus 10 meters by 10 meters, you're all of a sudden going from 1 square meter to 100 square meters. If you square root that, then it might be on a nice, easy linear scale. And likewise, cube root might be really useful if your response variable is a volume, cubic centimeters or cubic meters, whatever it might be. So let's just kind of play with those really quickly, just to think about what it looks like. And so here I'm going to simulate some data, right up there. I'm going to simulate some data where I'm just going to take random variables drawn from a normal distribution, and then I'm going to cube it. And again, that's just because I'm simulating the data. But let's say that we had some volume data. Let's say that it was cubic meters. And our data looks like this, right? And we look at that and we're like, that looks pretty skewed to me. I don't like how that looks. We might entertain trying, well, what would happen if we were to cube root that? Again, looking at that and assuming that this is, cubic meters, it's like, okay, it's skewed to the right. I'm going to put it, or I want to analyze these data. So what I want to do maybe is I want to cube root it. And so let's just look at what the cube root looks like. So raise it to the power of 1/3. And I'll make a little bit more breaks here. 10. Okay. So now we have more of our mass towards the middle. And we might eyeball that and say, I think that that actually looks a lot better than that looks. And again, it's totally fine. There's nothing wrong with that. We could also then, once we've transformed these data, we could calculate the mean of YY cube rooted. And so that would be the mean on that transformed scale. And then if we wanted to, we could transform it back, or back transform it, to the original scale. Because right now we are in cube root units, which is 10.7. And so if we were to take 10.7 and cube it, that's what we would say that the mean is of our data based upon our transformed data. Now this is different than the mean of our actual raw data. Right? And so when we had that skewed distribution, our mean was 1460, but when we transformed the data, then calculated the mean, and then back transformed it, this is our estimate of the mean. And so it's important to keep that in mind whenever you're calculating things like 95% confidence intervals. If you're doing that if you're doing your statistics and you're doing your statistical analyses on the transformed data, when you're communicating aspects of that sample, you want to make sure that you're keeping track of what units are you in, because when we cube rooted this right here, when we cube root that, we are now on a cube root scale. We are no longer in the raw units that we originally had. And so I can cook up another little example here. Let's say that I'm going to simulate length and width, which means, as you might imagine, I'm going to pretend that our response variable of interest is area. So I don't know what it's the area of. Maybe it's leaf area, who knows? But we have all these different measurements of area. And let's go ahead and take a look at our data, because the first thing that we would want to do is a little exploratory data analysis and say, well, what the heck does our data actually look like? And we look at that and we're like, that looks a little skewed right to me. I mean, we could even say, well, what does D'Agostino tell us? We could say normal test of our areas, and the method is DA. And then we look at this and it's like, well, we look like we're okay with kurtosis. Skewness seems to be a little bit of a problem. And overall, based upon our DA test, it really wants us to reject normality. Now again, we can't just blindly follow what the normality tests are telling us, but that test is giving us an idea of what we might need to fix. And it looks like skewness is something that we might need to fix. Again, our response variable is area. And so once you think about area, that's already in squared units. And so maybe that is the reason why we have this skewed distribution. So let's go ahead and transform our data. So I'm gonna actually create a new object this time called square root of area. And I'm gonna say that area, it's gonna be the square root of area. Okay, so now we have it in units that are square rooted. Let's take a histogram of that, square root of area. And now we look at that, that looks a heck of a lot more normal-ish compared to that. And I always refer to it as normal-ish because it'll never be perfectly normal unless you had an infinite population size or an infinite sample size drawn from a truly normal population. But you know, all models are wrong. Let's make a useful model. And so that looks a little bit better. And we could even ask, well, what does D'Agostino tell us about that? Like, did this work? So sqr.area within the D'Agostino test. Let's go ahead and we run that. And D'Agostino is telling us that it's pretty happy accepting the null hypothesis that our data are normal random variates. And so again, now we can go ahead and we could do any kind of analysis we want to do. We could make predictions. We just have to remember that we are in square root units now. We are not in our raw units. So that means that, you know, if we were to calculate like the 95% confidence interval around this, but then we wanted to go back to real units, we would have to back transform the upper and the lower parts of the confidence interval and back transform the mean. And that's what we would want to communicate to people when we're talking about our data, which means that we would have an asymmetrical 95% confidence interval because we will have back transformed it. And you can play around with that and get a feel for that. And so those are power transformations. They can be pretty useful. Again, when they make sense is especially when you're dealing with response variables that are clearly in cubed units like volume or in square units like area. Whew, having trouble here. Okay, the next kind of transformation that is extremely commonly used is the log transformation. And the reason why the log transformation is extremely common is because in nature, a lot of things tend to be log distributed. And so it's not an uncommon thing where if you look at your data and you plot it out, that your data will be skewed. And log transformations are really good for positively skewed data, as are square root transformations. And there's no reason why you should pick one over the other. It all depends on what you feel comfortable with. But again, log transformation is a very, very common one. The log transformation is simply, as the name implies, logging your data. Now, you cannot take the log of a number that is 0 or less than 0. So if your response variables are either you have values of 0 or you have less than 0, then you would have to add some kind of a constant to your data. And so, you know, normally, let's go ahead and let's see, what am I simulating here? So I'm going to just simulate a little data. Okay. Again, you don't have to worry about this. This is a log normal distribution that I'm taking random variables from, but all we're doing is cooking up data. So don't worry about the details of a log normal distribution. So I've taken my sample from nature, and of course the first step in quality control that you should always do with with your data when you start playing with it is have a peek. Let's take the histogram of y. And I look at that and I say that definitely does not look normal. That looks just so slightly skewed. And so let's see what it would look like if we were to log transform that data. So I'm going to go ahead and I'm actually going to say breaks equals 50 since we have a big enough sample size, so it looks like that. And now let's go ahead and take the log of that. And now I look at that and I think to myself, that looks pretty normal-ish. I feel pretty good about calculating the mean of that. And then I feel pretty confident I could estimate a 95% confidence interval around that. I really like that. We just have to remember that we are in log units. We are not in the raw units that things were measured in. And so let's go ahead. I'm so happy with that. I am going to say that my log y is going to get the log of y. Again, if some of our values of y were 0 or less than 0, we would have to add some kind of a constant to it. So a really common constant that people add to it, because oftentimes you can't have less than 0, like you can't count less than 0 things, or you can't measure less than 0 things. The common constant that people add to it is 1. So you would just add 1 to all of your response variables and then log transform it, and that's totally fine. I don't see any problem with doing that. We just have to keep track of what exactly our transformation was. And then, again, it's going to look the same, except in the underlying part of it, we added 1 to everything, and then we took the log transformation of it. We don't need to do that for these data, so I'm going to just go ahead and I'm going to just say that it's that. Okay, and so this is our new data. And so now I can calculate the mean. So we have our transform data, and if we wanted to then, if we're going to model it and we wanted to think about it, we could calculate the mean. So I'm going to say L mean will get the mean of Ly, and then I could also calculate the standard deviation of Ly. Okay, so now I'm in the log units. This is the mean in the log units. This is my standard deviation. So let's say that I wanted to calculate, say, the 95% interval for the data. Not the 95% confidence interval, but just the interval for the data. Well, we know that the upper would be what? It would be, we would start with our mean, and then we would say plus, and then 1.96 will be the magic number that we'll use from the normal distribution, multiplied by the standard deviation of Ly. And then we could likewise say what the lower part of that is. So that's going to be L mean minus 1.96 times the standard deviation of Ly. So we have the upper, we have the lower, and we have the mean. And that looks really nice and symmetrical. And so we can either present this data on a log scale. You could have your y-axis being a log scale, and that's fine. And so then we could say, okay, well, our mean is 10, and we expect 95% of our data to fall between 8.05 and 11.96. Or we could put it back into the original units that we used, or that we measured our data in. And so to do that, we could take the mean and exponentiate it. And so now it's going to be back on the raw units. And so our mean is now 22,167. And let's go ahead and exponentiate the upper limits. And let's exponentiate the lower. And so you can see that it's asymmetrical, right? Here is our expected number, the mean of our data, we expect 95% of the data to fall between 3,100 roughly and 156,000. Okay, and so it's asymmetrical. There's a much larger range from the mean to the upper than there is from the mean to the lower, but that's because we calculated all of these things when it was on a log scale, and then we've chosen to bring them back into the untransformed units, the raw units. So that's an important thing to remember when you're dealing with transformed data, is to pay attention and keep track of where or what unit you're in. So that way, if you want to communicate to people back into the raw units, that you have to be sure that you back transform all of the important bits that you did when you were in the transformed universe. Okay, now back to the previous little thread. The last one, well, almost the last one to think about is what's called a reciprocal I want to mention one other thing. This was on a log scale, which means that it sounds a lot like this. That kind of sounds like that might be the something similar to the geometric mean, right? Because we are taking the mean of the logs and then back transforming them. Okay, and so in that spirit, since that's kind of like the geometric mean, there's one that's kind of similar to the harmonic mean. And you recall that the harmonic mean is a reciprocal. And so we can use a reciprocal transformation. Let's say that you had something that was in units of rate, okay, and that yy now is our sample. And so we have all of these data, and they could be whatever per whatever. Let's pretend that they're a rate. Let's pretend this is, I don't know, kilometers per hour. We're looking at something that's really slow. Doesn't really matter. So we could go ahead and we could look at what our data look like, because that's always the first thing we want to do all the time, is let's take a peek at our data and make sure that we're happy with it. And again, we see something that's skewed. And there would be nothing wrong with looking at that data and saying, well, I'm going to log transform that, because I know that log transformations seem to do a good job. And maybe you're like, that looks a little bit more normal-ish. Maybe I'm good to go with that. Or maybe you decide that square root is good. I'm not totally thrilled, but it beats the heck out of the original one, right? I mean, that looks better than that. But then we could, again, think about what our data are. And if they are things like rates, for example, we might find that by taking a reciprocal of that, it might end up making more sense. So let's look and see what that would look like if we were to do a reciprocal transformation. Okay, so all I'm doing is flipping it up like that. I do a histogram of that, and then I sit back and I'm like, well, that looks more normal-ish than a log or a square root. Maybe I'm really happy modeling these data using the reciprocal of the response variable. And again, that's totally fine. You're not doing anything wrong. You're just changing the scale at which it's measured. You just want to make sure that you're keeping track of the fact that you're no longer dealing with your raw YY units. You're dealing with the reciprocal of your YY units. And so that is, that should all be kind of good and straightforward. And again, I just want to emphasize there's nothing wrong with transforming your data. Okay. So things like the power transformations and the log transformation and the reciprocal transformation, they're actually part of a whole family of transformations called the Box-Cox transformations. And I wrote a little text about the Box-Cox transformations, and I would say until you start feeling comfortable with transformations, that you don't worry too much about the whole Box-Cox family. If you just remember square root, log, reciprocal, those are fine and dandy ones, and that's all good. Alrighty, we're almost done. This next transformation that I want to mention, I'm only mentioning it because it's used a lot in the literature that's older than about 15 years. And you should at least be aware of it. So that way when you're reading papers, you understand what they were trying to do with this particular transformation. And also, if anyone ever suggests to you that you do this transformation, you can think really carefully about whether or not you want to ignore that person. And this transformation is what's called the arcsine square root transformation, where it quite literally is you're taking the arcsine of the square root of your data. And the objective behind this transformation is to deal with proportional data. So proportional data is going to be constrained between 0 and 1. And that can be a problem because, in theory, the normal distribution goes from negative infinity to positive infinity, which clearly our data, that's outside of the realm of possibility, but we can still feel good about modeling our data as normal. But with proportional data, it can become challenging because you can have data that's slammed up against 0 or slammed up against 1, and it's constrained there. And as a consequence of it being constrained there, you're never going to be able to really come up with an easy way to model that as a normal, maybe. As we'll see, there are ways to deal with that. But the old way was to do the arcsine square root transformation, which in principle made the tails long and more normal-like so that you could model your data drawn from a normal distribution. The problem with the arcsine square root transformation is that it really only works if your proportions are somewhere in the middle. Like if your lowest value is 0.03 or 0.3 and your upper value is 0.7, the arcsine square root transformation can do a pretty good job at making your data normal-ish. It becomes a problem when you have things closer to those extremes. The arcsine square root transformation doesn't really do that great of a job. When dealing with proportional data, there's alternatives, but to give you an idea that it's not just me that doesn't like the arcsine square root transformation, here is a paper that was published in Ecology in 2011. I gotta find it now. Where did I put that? Where'd it go? Where'd it go? There it is. And you can see that the title doesn't really pull any punches. It says the arcsine is asinine, the analysis of proportions in ecology. So if you have data that's proportional data, later in the semester we'll see how we're going to deal with that. There is a new kind of body of approaches called generalized linear modeling, where we are going to do what's called a logit link with proportional type data. And it's going to solve all of these, not all of them, but it's going to try to solve the majority of the problems of dealing with proportions in ecology. But we're not going to get to that till the end of the semester. So if anyone right now is working on data that's proportional data, and you're like, I can't wait till the end of the semester, send me an email and we can have a quick chat about that. But I didn't want to jump too far ahead. But yeah, arcsine is asinine. It's a pretty interesting little paper here from 2011, and they really kind of let people know what they thought about the arcsine transformation. I haven't seen the arcsine transformation in any real paper that for a really long time. So it's definitely totally fallen out of favor. I just wanted to mention it because it's still pretty ubiquitous if you dig into the older literature. This brings us to the I guess the last real transformation, and I call this transformation to be the nuclear option. And I call it the nuclear option because all you're going to do with a rank transformation, did I mention it? It's a rank transformation, is you're going to rank your data. So you're going to line up your data from the lowest to the highest value, and the lowest value is now going to be 1. The second lowest value is going to be 2, 3, 4, so on and so forth, right? So you're going to lose all of that information, and that's why I refer to it as the nuclear option, because you've dramatically changed the characteristics of your data by doing a rank transformation. And the serious problem with doing a rank transformation is that there's no way to back transform it. Once it gets ranked, there's no way that you can know what the first value was or the second value. With the other transformations that we've talked about, even the arcsine square root transformation, but certainly the log transformation and the reciprocal transformation and the power transformation, it's just an additional line of code, and we can back transform it to the original units. with rank transformation, we can't do that. And that's why I refer to it as the nuclear option. Okay? And we can rank transform our data. So I have, I'll just go ahead and I'll simulate some data here. And I can look at this, and there's no transformation in the world that maybe is going to make this look rank transform or make this look normal. And that really makes me sad. And so maybe I decide I'm going to transform that data, and I'm going to say, I'm going to just have it rank Y. And so now our original data, if you look here, we have all these different values that were drawn, right? This is our original data. When I transform it, now it's just a bunch of ranks. And there's absolutely no way that I can go back to the original data. I know that, this value is certainly greater than that value, and that corresponds to this and this. So 16.86 was the third smallest number, and 143.2 was the 62nd largest number, or however you want to think about it. But there's no way I'm going to be able to back transform that. And so that's why I call it the nuclear option. It should only be done out of sheer desperation because your data is so ugly. And as you become more and more kind of skilled at statistics, as you continue your journey through the field of statistics, you'll see oftentimes there are solutions that they're kind of beyond what we're going to do in this class, but there are often solutions that actually allow you to back transform out of really, really messy data. And so you only want to do rank transforming as just desperation last moment, because again, nuclear option, you're permanently losing all of maybe the interesting bits, all of the cool little parts of your data are now gone like tears in the rain. Okay, and then the final thing that I mentioned on there, we've already talked about that, which is standardizing your data, which is simply putting your data where it's centered at 0 and then divided by the standard deviation. So it's a Z transformation. Z transformation, all it's doing is it's changing the units of your data into units of standard deviations. And standardized data, or scaling our data, I promise will be our friend, because it's very interpretable to kind of compare things when they're in units of standard deviations as opposed to if they're in the raw units. And so that's it with transformations. So feel good about transforming your data if you think you need to transform it. You do not need to justify to anyone why you've transformed your data. Period. So if anyone says, well, why did you have to justify why you log transform that? All you have to say is, no, I don't want to, because I don't have to. Yeah, so if that opportunity ever comes up, let me know. I'm curious to see how it goes over. All right, that's it for our little bit of housekeeping, and now we will just sit and ponder the wonderful world of the normal distribution.